Hello everyone, I'm James Hong from POSTECH, South Korea. Today, I will talk about artificial intelligence-based network management. In this talk, I will mainly explain the network intelligence project that my research team has been carrying out for the past 4 years. This project is funded by the Ministry of Science and ICT in Korea. And the listed contributors are members of our research team. In this talk, I will present challenges that are faced by telecom operators. I will then address the recent SDN NFV technology trend. After that, I will introduce what artificial intelligence is and how AI technology is being applied in network management. Specifically, I will introduce AI-based NFV lifecycle management technology, which has been studied in the DPNM laboratory for the past 4 years. Finally, I will introduce AI-based traffic engineering and summarize this talk. This is my brief bio. The networks have been growing larger and more complex over the past several decades, while adopting new technologies and services. Telco networks around the world typically consist of hundreds of backbone routers, thousands of edge routers, and hundreds of thousands of access switches. As shown in this slide, telco networks are built as either best effort networks to provide general web services such as email, web surfing, or premium networks to support high quality services. In particular, premium networks are used to provide enterprise services such as VPNs and IPTVs, requiring high reliability and high quality, as well as mobile services such as 4G and 5G. In recent years, thousands of middle boxes or network function boxes are being virtualized based on cloud computing and NFV technologies to support and perform various network functions such as BSS, OSS, NMS, EMS, network address translation, DNS, firewall, DPI, IDS, IPS, and so on. In telco networks, traffic volume began to grow around 2007 drastically when smartphones began to spread worldwide. The data traffic is still growing more than 20% per year. In the case of mobile communication, data traffic was mainly audio in the 2G era. However, with the advent of smartphones and mobile communication services through 3G, 4G, and 5G, most of the data traffic has been audio, video streaming, and web browsing. Although telcos continue to increase network capacity to cope with the increase in traffic, reduction of CapEx and OpEx is a challenge for telcos as global subscriber growth continues to decline. In the 2G era, there was a competition between telcos to attract subscribers, and there was no other competitors. Thus, telcos were able to earn stable revenue. However, with smartphone era, changed the situation a lot. New content and service providers, such as internet players like Google, Amazon, and Facebook, have emerged as powerful competitors for telcos. they were much more innovative in their operations and fast time to market than telcos. It might be due to manpower efficiency, differences between service providers and telcos. However, the main reason was that telcos used a hardware-based communication system that was less flexible, so it took much longer to develop and provide new services. After all, telcos invested a lot of money to build high-speed wired and wireless networks, but they could not earn more revenue. Instead, internet players such as Amazon, Google, Facebook, and Netflix have made high revenue by using these networks. Internet players such as Amazon, Microsoft, and Google do not build networks themselves. Instead, they build data centers or rent cloud computing resources to provide services. When building a data center, they design hardware themselves and make vendors compete to develop them at low cost. After that, internet players then select a vendor that provides the cheapest hardware. In addition, open source software such as Linux operating system, Apache web server, and MySQL database is used to build a dynamic and flexible infrastructure. Thus, internet players can deploy their infrastructure dynamically and flexibly at a low cost. On the other hand, telcos have built networks composed of expensive hardware-based entities and have operated services on the infrastructure. In addition, it was hard for telcos to adopt new technologies quickly due to vendor dependency and incompatibility issues of network entities. As a result, telcos are aware of the need to change their networks and service environments into a similar and competitive infrastructure of internet players. In addition, telco networks require much more middle boxes than backbone routers because the networks should provide various types of services with high speed, high reliability, and high quality. Please note that a middle box is a generic term used for systems that are yellow boxes in this diagram. However, these middle boxes are very expensive and have hard time of updating new features on them rapidly because it is necessary to coordinate with vendors. Various future internet technologies have been developed over the past decades to solve the problem. Among them, SDN, NFV technologies that enable telcos to reduce CapEx, OpEx have emerged and attracted attention. SDN NFV has laid a foundation for rebuilding software-based infrastructure by reducing or by replacing expensive hardware-based entities. However, it does not mean that the problem is already solved. Instead, I'd like to say that this infrastructure enables us to begin trying to solve the problem. As you may already know, SDN is a technology that separates the control plane from the underlying data plane of the communication system. It allows the control plane that is complex and hard for implementing to be operated in a centralized manner based on cloud computing. Thus, it is possible to build networks without expensive network entities. In addition, SDN supports network programmability and provides vendor neutrality by building software-based infrastructure. Network function virtualization, or NFV, is a technology that significantly reduces CapEx and provides easy-to-use network functions by leveraging open source software from white boxes instead of using expensive middle boxes described in the previous slide. With a combination of SDN and NFV, middle boxes can be implemented and managed as virtual network functions, or VNFs. SDN can make connections between VNFs flexibly for service function chaining, or SFC, and apply auto-scaling that adjusts resources allocated to VNFs in response to traffic changes. Thus, SDN and NFV has the advantage of enabling powerful and flexible network operations. The introduction of SDN and NFV has drastically reduced costs while enabling flexible and dynamic infrastructure operations. However, network scale and complexity have also increased significantly due to SDN and NFV. Specifically, virtual machines run VNFs, so there are numerous VMs in networks, making it human operators hard to handle them manually. In addition, the transformation from hardware-based to open source software-based environment causes vulnerability issues, generating network failures frequently. As a result, it is too difficult to manage the complex networks by human operators. Thus, R&D approaches using AI have been proposed to solve the complicated network management in the past few years. AI is a computer program or a system that artificially implements a human's ability to learn, infer, and perceive. The representative example showing the effectiveness of AI was a famous Go match in the spring of 2016 between Sedol Lee, the world's #1 Go player, and AlphaGo, which is a Go software developed using AI. As you know, AlphaGo won by a landslide victory of 4-1. In addition, AI is a key to the success of a self-driving car that many companies, including Tesla, are developing. In general, the terms such as machine learning and deep learning are commonly used to describe AI. However, natural language processing, or NLP, technology is also a big part of AI technology. As mentioned in the previous slide, AI is a technology that makes a computer think like a human. Machine learning, the part of AI technology, is a program that analyzes data statistically and makes decisions or predictions based on the analysis. Deep learning is a machine learning approach that uses artificial neural network to learn data deeply, i.e., multiple iterations, by using high-performance servers such as GPUs. Natural language processing, or NLP, is a technology that enables machine, example computer, to understand and describe human language. This technology is also used to analyze massive text data, for example, log data stored on network entities. To briefly explain the difference between general programming and machine learning, it is as follows. In programming, when a person puts input data into a program, the program processes it and outputs the result. In contrast, machine learning uses input and result values to generate models that perform similar functions to the program. After that, the generated model is used to print output as a result of new input data. Let me give you a more detailed example. As shown in this slide, this is a picture of a cat. First, we input the cat picture into a machine learning model. For this, we convert the picture into pixel data and input it into the model. Second, the model outputs results by computing the input data and the weight of the model. The model determines whether the picture is a cat or a dog, compares whether the result generated by the model is the desired result, and then feeds back to update the model's parameters. If they are properly updated through hundreds or thousands of feedback processes, the output value of the model can accurately classify the cat's picture. Machine learning can be categorized into supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is a method that uses feature and output data, labeled data, to learn a model. This method is used to classify or predict data. Unsupervised learning is a method that uses feature data only to learn a model. This method is used to cluster data and discover hidden pattern from data. Reinforcement learning is a method that uses input data or environment and reward values to learn a model. This method is suitable for implementing decision-making models used in games and robot control. Let me explain supervised learning in more detail. Supervised learning is a method of learning that uses labeled data. This method identifies relationships between input data or feature data and labels. The figure on the left below is an example of supervised learning. This example inputs the picture of 3 apples and the sentence, "These are apples," into the model. If the model is well trained, it can predict it's an apple. Supervised learning is mainly used to generate regression model and classification model. Unlike supervised learning, unsupervised learning does not use labels. The figure on the left shows that unsupervised learning clusters data with similar characteristics. The figure on the right shows a comparison between supervised and unsupervised learning. In supervised learning, it classifies data as red and blue labels. On the other hand, unsupervised learning is used to cluster data with similar characteristics. Because labeled data does not exist, unsupervised learning cannot classify data into specific classes. Reinforcement learning is a method that trains an agent to maximize the cumulative reward in a given environment. This method defines state and action. The state is the agent's status, and actions are options that the agent can take from the state. In reinforcement learning, an agent obtains reward value when taking one of the actions from a given state. The agent learns to take appropriate actions so that actions taken in states result in maximizing cumulative rewards. So far, I have introduced what AI is. From now on, I will explain what AI-based network management is. The main goal of this is to handle the growing complexity of network management by using AI. By applying AI technology to network management, we can identify a correlation between complex network events quickly and predict future events. Unfortunately, we will be able to implement the self-driving network that manages the network without administrative intervention. AI-based network management system requires several components. First, it needs a data collection and processing system. It is necessary to implement a monitoring system that collects and processes data from network devices because AI learns using the data. Second, it needs AI models to understand complex network management policies and learn network data. Finally, it needs a management system that is responsible for continuously improving the performance of AI models. It also applies and orchestrates policies generated by AI to network management. We can classify AI models for network management according to their roles. The first role is to help administrators determine policies by analyzing or predicting data. This model can provide administrators with useful information by analyzing the cause of network failures or predicting resource utilization. The second role is to manage the network by learning management policies. This model can carry out traffic engineering by detecting traffic change, deploy VNFs to appropriate locations, and adjust the amount of resources allocated to the VNFs in response to traffic. My research lab of POSTECH has been working on AI-based network management in SDN and NFV environment to develop an NFV lifecycle management system. I will introduce this research to you. the NFV Lifecycle Management System provides several functions. Among them, I will explain how main functions such as VNF deployment, service function chaining, auto scaling, and anomaly detection. NFV management and orchestration, or MANO, system is responsible for managing the NFC lifecycle. This system monitors NFV infrastructure, running VNFs, and applies management functions decided by AI models. This slide shows an example of the NFV lifecycle management process. VNF deployment deploys VNFs in servers in an optimized manner. Service function chaining schedules and invokes VNFs to provide a service. Auto scaling automatically creates more resources to create or delete unnecessary resources that maximize the efficient use of resources. Finally, anomaly detection detects VNFs that do not behave correctly. All of these are done using more accurately and efficiently using AI techniques. First of all, we have built an NFV testbed that mimics a telco environment with data centers and edges in order to develop an NFV lifecycle management system. We configured the testbed by considering various scenarios that can occur in an edge computing environment. For this, we distributed the physical locations of the servers and emulated different delays between them. Our testbed has 3 AI nodes, 1 monitoring node, and 1 controller node. The AI nodes learn data collected by the monitoring node, and then the controller node applies network policies generated by the AI nodes to the environment. The network intelligence study that defines AI-based network management architecture was published as a TNSM journal paper in August 2020. In this research, we developed the NFV monitoring module. It leverages open source software to collect virtual network data, virtual machines, and containers data, and VNFs and CNFs data within the NFV testbed in real time. We also implemented a monitoring function to measure VNF packet processing time. This module enables the management system to collect fine-grained data from network devices in real time. This work was published in TNSM CNSM 2020. We developed a VNF deployment function. The goal of VNF deployment is to reduce network operating costs by placing a VNF instance on the optimal physical server within the edge computing environment in response to traffic changes. We use topology data and traffic data as feature data, and integer linear programming, or ILP, is used to generate ground truth data, i.e. labeled data. We used feed forward neural network, or FNN, and graph neural network, GNN, for learning traffic data and topology data, respectively. The model makes the optimal VNF deployment, and this output lets us know where to deploy or remove VNFs. We evaluated that compared to labels data generated by ILP. This algorithm installed and removed VNFs on optimal physical servers with 91% accuracy. You can see more details of this study in our CNSM paper shown at the bottom of this slide. We also developed the service function chaining, SFC, function using AI technology. This algorithm selects VNF instances deployed in an NFV environment, creating an optimal SFC path. We developed the AI model for service function chaining using Q-learning, one of the reinforcement learning models. The method obtained reward values considering VNF placement locations and resource utilization such as CPU and memory allocated to VNFs. We evaluated that compared to a random algorithm, the Q-learning that considers CPU utilization only, the SFC algorithm could select a much better SFC path. You can see more details of this study in our APNOMS 2020 paper. We developed an auto-scaling function using Deep Q Network, or DQN, one of the reinforcement learning algorithms. This method consists of two models: the DQN model to determine adding and removing VNF instances composing network services, and the decision model to place the VNF instances in the appropriate servers while considering an edge computing scenario. In addition, the decision model chooses one of the VNF types to be scaled to minimize scaling costs. We evaluated that this auto-scaling algorithm maintained an SLA violations rate of less than 2.33% in response to traffic changes. You can see more details of this study in the IJNM journal paper shown at the bottom of the slide. We developed an anomaly detection function using XGBoost, one of the supervised learning models, to detect VNF's abnormal status. XGBoost calculates fast and prevents overfitting by using ensemble learning to train decision trees. This method detects SFC composed of VNFs causing SLA violations and finds the location of VNF causing SLA violations. In the evaluation, the detection accuracy of our model was about 93%. You can see more details of this study in our CNSM 2020 paper. We created a model that predicts failures of virtual machines operating virtual network functions on the NFV testbed. The model uses logs collected from the VM as input to predict if the failure will occur within minutes. To learn the model, we constructed SFC and collected logs from each virtual machine on the testbed. Attacker proceeded with the attack to overload, and state checker sent ping to each VM to determine if it had failed. To use log data as input to the supervised learning algorithm, CNN, we transformed log into a matrix with word embedding and trained the model to calculate the probability of failure within minutes. As a result of the learning, our model predicted the failure 5 minutes in advance at 67% of the F1 score. Lastly, I will introduce AI-based traffic engineering. We developed an AI-based traffic engineering algorithm using Q-learning. In wide area network connecting data centers, this algorithm is responsible for link failure recovery through detour paths in the link failure events. It also provides load balancing. This method could improve the average link utilization while providing the shortest paths in response to link failures in real time. The figure on the left shows that the algorithm determines detour paths to recover link failures, red links. In addition, the figure on the right presents that our method distributes multiple traffic properly in the mesh network. The wired and wireless networks are rapidly evolving with the advent of new technologies. In addition, data centers based on cloud computing and proliferated and play a significant role in many areas. Telcos and service providers operating large-scale networks and the data centers have used to reduce CapEx and OpEx. As the networks grow larger and more complex with the introduction of NFV technology, it is hard for human operators to operate large-scale networks. Thus, it is necessary to apply AI technology to manage complex networks. Ultimately, telcos want to build a self-driving network. To achieve this, AI-based network management research has just begun, requiring more research and development. How about joining this attractive research area? We have been making our research results available as open source software. If you are interested in using our software, please download them from our GitHub as listed here. Well, this is end of my presentation for today, and I thank you for listening. Do you have any questions?